So yesterday I defined Monge-Ampère operator in this form. OJ. Oh. So this matrix looks a little bit strange. You have second order derivative, first order. But there's one other way to look at. So again, yesterday I defined a metric. It's a dd bar of log of law. So here dd bar just means complex Hessian. So I can see this as a matrix. Or if you prefer, you can see this as a scalar form. So this defines a metric. So in this situation, if you take determinant of this metric, so this is a second derivative, so you have many negative power of rho. So it diverges at the boundary. So I have to make it smooth by putting this power. Okay? So now it becomes smooth. And this is J rho. Okay? So, but in this definition, you have to once pass to some metric which has singularity, and then kill the singularity using this. So this operator looks better because there's no singularity at all. So this is the usual, say, this may be the usual Monge-Ampère operator because you are applying Hessian and take determinant. But you have singular term here. So this is another way to write J rho. But this is very helpful to understand what's the rich tensor of this metric and why Monge-Ampère equation is equivalent to the Einstein equation. So we're going to solve equals, Ricci equals Ricci equals minus n plus 1 of G rho. Of course, this is a Ricci for G rho. So this is the Einstein equation. Okay, this is equivalent to J rho equals EF, where dd bar F equals 0. So the special case is F equals 0, then this is 1, so it can be usual Monge-Ampère equation, but you can put any pre-harmonic function there. It doesn't change the metric. So why this is so proof? This is clear from this, almost clear, but so take the log of this equation. Take log. Then you have this side, you have log. Okay. Log n plus 1 times plus log determinant G rho equals log of J rho. But here I assume that this is E to F, so this is F by definition. Okay. Now apply dd bar. Then this term gives n plus 1 times G rho. Okay, this is the definition. And this gives Ricci. This is again definition, Ricci of G rho. And this is just dd bar F. Okay? So if this satisfied, then this side vanishes. So F becomes pretty harmonic. if f is pre-harmonic, then this is 0. That means this is Einstein. So this is the Einstein equation in terms of defining function. So the choice of f is not important at all, because if you consider another metric like this, but this is nothing but dd bar log rho plus f. But dd bar kills f, so this is g rho. So if you consider metric level, this scaling is irrelevant. So you can just fix any scale you want to simplify computation. So I put f to be 0 and consider the equation equals 1 on omega, and u equals 0 on the boundary, and u positive on omega. Let me call this Monge-Ampère equation with Dirichlet boundary condition. Okay, this is the equation we're going to solve. Okay, here's the existence theorem, starting with Fetterman, Chang, and Yau, and Lee-Melese. They prove that there exists a unique solution MA. You see, unfortunately, this is not smooth, omega. And smooth inside, but not smooth at the boundary. So it just lose some regularity. And but the good thing is this is unique. And U has asymptote expansion near boundary. So U starts like just smooth defining function plus sigma rho to j equals 1 to infinity eta j rho n plus 1 log rho to j. So this j is not derivative. So I don't use derivative notion anymore. So here eta j is smooth up to the boundary. Okay, so this means the definition, you have precise definition, but that's not the point in this talk. So you can choose good defining function, which is almost a solution, but you have to add some such a singular term to make exact solution. So there's no convergence, but there's a symplectic expansion. The point is the number of power. So rho to n plus 2. So and log rho. So the regularity is n plus 1 plus something, but not n plus 2. So you can get smooth one in general. And if maybe this is good enough for now. Okay. So we have existence. So as a corollary, strictly pseudo-convex omega admit unique Kähler-Einstein, unique complete Kähler-Einstein metric G H equals minus n plus 1 G, and this G is just this. Take Monge-Ampère solution, then this metric gives Einstein metric. And here I have to choose this minus n plus 1. So So yesterday, Datao said that you can always normalize this be +1, -1, 0, but here you cannot do this because we only consider this special type of defining function, and so if you do this, you cannot change the number. Okay. Yes, a natural choice. Okay. So the good thing is if you have two domain which is bi-holomorphic, then each domain has G1 Kähler-Einstein. So let me call it Kähler-Einstein, KE. So we have a metric here, and here two Kähler-Einstein. So same map gives isometry. So like the Bergman metric, any biholomorphic map gives isometry for this Einstein metric. So you can use this Einstein metric to construct invariant. Okay. So in this case, the construction solution is not so easy, but I later show you that the smooth part, this part is computable. So we mainly use this. Okay. So the remark. So now we have two metrics, omega pseudoconvex. We have Bergman metric and Kähler-Einstein metric. So natural question is when this agree, or when Bergman metric become Einstein, but this is known that this is a whole if and only if to the ball. So again, for the ball case, you can write down everything, but that's the only case you have the equality. So for other cases, there's some difference. We will compute the difference maybe tomorrow. Okay. So as a metric level, everything clear. But to do a simplific analysis, we have to work within the defining function level. So working in defining function level means I have to care this scaling factor. We have to carefully choose the defining function by choosing the scaling factor. Okay. So let me write down translation rule. Of Monge Ampère solution. So for each domain, you have a solution here and here. The pullback is not a solution. You cannot just pull back. Then you have to scale it by using Jacobian. So for the metric level, that's okay, but here you have to be careful. So I will explain how to compute the transformation rule. So in general, for U, so U will be later taken to be a solution, but here U can be general function. So any real valued function set U hash on this bundle omega to R. So C hash means C minus 0. Maybe C cross will be better, but I use hash. So C star for this. Then this is given by, so this additional variable has Z naught. So this is Z1 to Zn. So we have one more variable. Then this definite U hash is defined by Z by definition, just multiplied by this. So add one more dimension and put this factor. And it looks nothing, but it's very helpful because if you compute the Hessian now j, k runs through 0 to n. So 0 is included. So now this is a n plus 2 times n plus 2 matrix. Okay. Just compute this. So 0 derivative just hit this. So first column, the first row hit this. And here you have u, and this part is just a Hessian of u. It's quite easy to know, check the determinant of u, zj, u, zk, conjugate, square, zj, zk bar. So here, got the same Monge-Ampère operator again. So this is ju, oh no, some factor equals minus 1 n, and should have z naught 2n, because there are many undifferentiated z naught, so it should be factored out. Here you have, so this is just z naught 2n j u. So this is another way to get this strange determinant. This is actually coming from the Hessian on this bundle. So this is another way to understand the Monge-Ampère operator. Okay. So the lemma, trivial lemma now is that ju equals 1 if and only if you lift up. So let me define this side by lift up version. Everything with hash. Hash u hash equals z naught 2n. Okay. So you have one more dimension and scale it nicely, then it becomes this usual complex Monge-Ampère equation. Okay. Now, I claim that this u hash transforms nicely, or this u hash is invariant under Pruback by bihomorphic map. But then I have to define what is the bihomorphic lift to this bundle. Okay, so suppose you have a bihomorphic map. Okay, it should be the okay. A bihomorphic map. Then I want to lift up this to bundle map hash c star times omega 1 to c star times omega 2. So this is given by z naught z mapped to here z naught fz. So I also use notation that this is w0w for the image, and here phi is equals determinant f prime z. It's fractional power. Okay. So take Jacobian, then take this fractional power. So there's some branch, but that you can choose any branch. So we only do some local calculation. It doesn't matter. Anyway, we only use the norm of this. So, but important thing is that locally, this is holomorphic. So this bihomorphic map lift up to this bundle. So if you know about complex geometry, so this hash times omega is nothing but the k canonical bundle n plus 1, 1. And maybe 0 removed. Okay. If you prefer invariant way of writing the canonical bundle, and then the pruebach is just a Jacobian. So we have fractional power, and this is a push forward, so you have negative power. So usually such bundle doesn't exist, so the lift doesn't exist, but you don't have to worry about this point. I don't use global section. Okay. So we have lift up. So compute the. So first, let me compute the Hessian, Jacobian of this lifted map. It's quite easy. Determinant of, here you have phi and z naught dj. No. Here you don't have to compute. This is not important. So here just Hessian. And there's 0 because zeros. Okay, other components doesn't have z-naught reaction. So this is just phi determinant. The Jacobian phi. So by definition of phi, this is phi minus n minus 1 equals phi to minus n. Okay. So now compute j hash u hash pruebach by f hash. Okay. This is the usual Hessian plus minus. So this is given by Hessian pruebach times determinant of hash square. Okay, so you can write down transformation row of the complex Hessian that's contain Jacobi matrix. To take a determinant, you should have this. Okay. Then this term is phi minus 2n. Now we take absolute value, so you don't have to worry about the branch. And this is a pruebach, so you have pruebach has this phi, and also have to compute the pruebach of this scaling factor. This is just by definition 2n equals z naught 2n times phi 2n. So the point is that if you pruebach, so this is a pruebach this and pruebach this, you have the same factor. It should come here. So this is the way we have pruebach. So we have to pruebach this by f, pruebach this by f sharp. You get the same factor. This should appear in this side. So we observe that this u hash z naught square is equivalent to u hash j hash should be w. So now So U is omega 2 to R. Okay. So this should be W, 0. So on the targets, in this this is the W coordinate. So prove back this, you got just a prove back of function. So you have the same equation. This means Monge-Ampère solution. Let's have proposition. U1 and U. So if Uj is the Monge-Ampère solution for omega j, then U1 hash equals U2 hash put back by hash. Okay. So if you lift up, the solution is preserved. So this solution is invariantly defined. What is the meaning of the n plus 1 root? I will explain later. For this is coming from the universal bundle of a projective space, but here this is just it works.
Okay. What you mean by so this determinant of f times is a complex value function, right?
Which one?
At the bottom of the last board.
Yeah.
So the determinant of f times is a complex value function.
Yeah.
And you are taking its n plus first root.
Yes. Yes, locally you can take it.
Okay, so it just exists locally.
Yeah, exists locally. If omega is simply connected, you can take globally. Okay. But here the point is you only use the absolute value.
Okay.
So this formula holds for globally. That's always. So you have a good. So now this is the transformation rule for the lifted one. Then I have to write down what's happened for the domain. So U2 hash equals Z naught phi square. This is just writing down the definition. U2 hash prove back by F hash is this by definition, and Z naught square phi square Z U2. So write in this form. Then this part should be, this should be U1 because solution is unique. So the Monge-Ampère station equation downstairs and the equation on the fiber sister bundle is equivalent. So this pullback is a solution. If you factor out, this becomes a solution for the Monge-Ampère equation on omega 1. So we have U2, which is better? U2 pullback F equals phi I have to minus 2 U1, and this is determinant of minus and plus 1. Should be okay. So this is a transformation rule. So if you pull back, you have this scaling factor. let us compare this with the transformation rule of the Bergman kernel. So for the Bergman kernel, if you prove out Bergman kernel by homework map, you have maybe what was the definition? Okay. So this will give determinant squared. No, minus B1. Which is the right one? If we pull back here, so it should be negative, then it should be positive because F is, okay, here's negative. This is correct. So I'm taking negative power, so it should be positive. Then of minus n minus 1. So we know that leading term of V1 is u to the minus 1 minus n minus 1. So it should have the same transformation rule. Yeah, it makes sense. So this is another reason we have to take this power, because Bergman kernel has this transformation rule, and this is so Bergman kernel is u2 minus n minus 1, so you have to take a root. This is a good explanation. Yeah. So you cannot change this power. So we have a unique defining function. Unfortunately, this is not smooth, but unique, and it satisfies good transformation rule like Bergman kernel. Okay. So I can use this. Now we have make a bundle, so I can use that U sharp to define another metric. So let me define G tilde of U to be minus of JK. Now move from 0 to N, U hash. Okay. So now this is a metric on C times omega, or we can extend this up to the boundary at least. Okay, so this is better in a sense. We don't take log anymore because U hash itself is invariant, so you can define metric by using this. So there's no hash, so there's no log, there's no singularity. It is at least n plus 1 differentiable, so it is well defined up to the boundary. So this is another metric. But unfortunately, this is not Riemannian. This defines Lorentz scalar metric. This is called ambient metric. This is due to Fetterman and maybe Robin Graham. They wrote a book called The Ambient Metric. That is mainly about the conformal geometry, but the origin comes from this. So why this is Lorentzian and what this means? And also one more thing. So this is not just scalar, but this G tilde U is Ricci flat. So Ricci tensor equals 0 because determinant G tilde is just determinant is say plus minus of J hash plus or minus, I don't care. It's by definition, negative of this is the metric, so take a determinant, so you have n plus 2, so there's nothing, good. And take log, and apply dd bar, then dd bar log. But this should be z naught. Okay, lifted version. So if ju equals 1, this is just a z naught 2n. So this is going to be 2n, but this is definitely pre-harmonic, so you got 0. So this is Ricci. This side is Ricci. Ricci curvature for this is defined by minus of this. So you got this. So you have a Ricci flat metric. So to explain the meaning of this new Lorentzian metric, let me compute this for the ball. Okay, case example. So omega 0 is, so u is 1 minus z squared is the ball. So this is the Monge Ampère solution. So I can use u for this, but I prefer use rho for something smooth defining function. U may not be smooth. Okay. In this case, what is rho hash? Rho hash is just z naught square 1 minus z. Okay, so you can just compute, but there's some nice way to see. This is a good point to explain what is that bundle. So now we have C star times omega. This is bundle over omega. So this is ball. And this sits in Cn. And this can be embedded into Pn, projective space. So this is given by, for Z, embed this into Z. So homogeneous, using homogeneous coordinate, putting 1 in the first slot, then this becomes a point in the projective space. And by definition, projective space is a quotient of Cn plus 1, removing 0 and by the lines passing through 0. Okay. Then you can embed this into here. So now we have z naught z. In general, this goes to z naught z, not z. Okay, we want to make this diagram commutative. So I have to put z naught here to make this equivalent to this one. Okay, if you take a quotient, so z, you divide every coordinate by z naught, which is not 0, that gives this. So this is a commutative diagram of embedding of ball into Pn. Okay, so this is the coordinate z0, z1 to zn. Okay. This is homogeneous coordinate. So this project down to z0, 1 z n. Okay. So let me write down this low hash in terms of these homogeneous coordinates. Okay. So G z naught equals z0. I have to write in the other way. So z naught equals z zeta 0, and j should be zeta j divided by zeta 0 for others. Okay. So substitute this into row hash. Then row hash equals z naught squared 1 minus z naught z1 0 squared. So we can cancel out this, and finally you get square. So the metric, this is for flat case, so this is a model case, I put 0, is given by minus of dd bar row hash. So that means in matrix notation, this is just minus 1, 1, 1, 0, 0 everywhere. So signature is N1. Okay, this is a flat Lorentzian Kähler metric, Lorentz-Hermitian metric. So in this setting, you can define special unitary group of the signature by F hash in SL n plus 1 C. So this is acting on this space. Oh, I should not put this. The quotient already means this, so this should be the bundle. So this is a universal bundle. So universal bundle should not be called. Yes, this should be, I should write. Okay, this is correct. Okay, let me erase this part. Okay, so by F hash is linear map with determinant 1 and preserve G naught. So this is just a Hermitian metric on the linear space Cn plus 1. So this is the usual special unitary group. So this F, let me continue here. Okay, so we have a Cn plus 1 and Pn, and this Su for G. So I also use the notation. This is the Su for G. Okay. For this matrix, it depends on the choice of the matrix. The same group has different representations. So let me use this. And it's simpler. So it's acts on here as a linear map, and also acts on here as fractional linear transformation. This is a linear transformation. So the linear map preserve lines, so it is also acts on here. And since each element, So f hash acts as a fractional linear transformation f. So since f hash preserve this, so f hash map this to this. So linear fraction transformation should act on f. And this is invertible, so this f is in automorphism of omega 0. So we have a good description of the automorphism. And this is not uniquely determined, so n plus 1, it should be n plus 1, n plus 1 matrix. Should be good. Maybe better to have 0 here. So diagonal matrix acts trivially. So if you consider linear fractional transformation coming from diagonal, so this is something lambda identity n plus 1, and lambda to the n plus 1 equals 0, equal 1. So this contained in this SU, but it gives a identity map, so you have some ambiguity, but this is just a center of this and discrete finite group, so just leave it there. And so I can say that this special unitary group acts on the ball as an automorphism. So I haven't proved the surjectivity, but this is easily shown by, say, using Bergman metric. Okay, so in this setting, there are many things I can say. So what is this? What is this bundle in general? So this is called universal bundle. And this is considered canonical bundle of Pn. This should be the n plus 1. This should be the power. The universal bundle is a fractional power of canonical bundle. This is true for the projective space. So, but in general, this is not true. So if the but this explains why you have always a fractional power of determinant Jacobian. So this is a flat model. If you start with a model ball, you have a flat Lorentz scalar metric, and that's agree with this definition of ambient metric. So we can say that the ambient metric, a curved version of this model. Okay. I have 10 minutes. Let me say how to calculate the smooth part of Monge-Ampère equation, Monge-Ampère solution. So that's very important. Fetterman theorem. It's a C-infinity defining function of omega such that if you apply J, you have one, not exactly one, but the error term of this. So this means smoothly divisible by this. Everything is smooth, so this means divisible by factor of some smooth function. Moreover, such rho is unique modulo O rho n plus 2. So if you want to stay in the smooth category, you cannot solve the equation completely. But putting such an error term, it has solution. It's not unique, but the unique modulo this. This is big enough, so you can do differential geometry using this. Okay. So, and also you can calculate this. So here's a procedure. So start with take construction. There's algorithm. So start with take any defining function. Then set U1 to be rho times J rho this fractional power. Then should be rho J rho 1 equals 1 plus O rho. So it's a first order solution in a sense. Then inductively define UK plus 1 to be rho k times 1 plus 1 minus J rho k plus 1 minus k plus 1 for k equals 1 to n. Then you have J rho k equals 1 plus O2 rho k. Quite explicit. And the point is that there's some number. As long as this is not 0, you can continue. But unfortunately, when k becomes n plus 1, you cannot, the procedure stops. So you cannot go further. And this is exactly the point you got the log term in the Chang-Yau solution. So it is consistent. So actually, you can use computer to compute, actually write down these. So if you want to compute curvature of the metric, run this procedure on Mathematica also, and if you have enough memory, you can write down. I actually did this when I was a graduate student. At that time, there was very limited RAM, but still I can compute part of it in dimension 2. Now you have a good computer, so it should be possible to do many examples. Okay, just let me write down 2 basic equations, how to show that this is true. So there's a elementary theorem. So first equation is, so rho is any defining function. Phi is any infinity function. Take any smooth function. Right. So multiply defining function by, say, in this case, it's non-zero. Then maybe it's okay to have 0. Then this comes out. This factor plus O2 rho. This is just a linear algebra. So you calculate the Hessian and just compute the determinant. It's quite easy. The second, so this one, it gives first step. because this factor comes here, then it should be negative. It should be negative, otherwise it doesn't cancel out. Yeah, it should be negative, otherwise it doesn't cancel out. Yeah, this one. Put this, then they'll cancel. Yeah, it makes sense. Sorry about this. Okay, the second one, which proves this, is like J rho to phi rho to K. So if you modify the defining function by at the order K, then you have J rho times 1 plus K n plus 2 minus K phi rho K minus 1 plus O rho K. This requires more computation, but basically this is just a linear algebra. Apply Hessian to this and write down big matrix and try to kill terms expanding in the first row, then you get this. So this one, so if you have, this calls induction. This should be K plus 1, but the number should be same. Okay, if you do this, you have a solution. You want to modify this term by adding something to this. Okay, this term should be, so when this is 1 plus phi rho to K, this term means phi times rho K. Okay, phi times rho K. Okay. So this phi times this one should becomes here. The number is different. There should be some trick here. Okay. The one difference is here I factor out one row, but here I didn't factor out, so there's one difference. So it's a little bit confusing. Sorry about this, but in this formula, it's better to factor the defining function. Here I haven't factored, so if I factor row out, then this should be K plus 1 plus this minus 1 should make sense. Yeah. K should be replaced by K plus 1, then you have the same number. So using just these two formulas, you can inductively show that this is the solution to this order, and this should be unique in each step. So it's very nice. So if you want to approximate solution to some order K, you only have to do this K step. So it's doable, but actually you want to compute something, there should be more trick. If you want to use the quadratic term, you can throw out the higher order degree term from a determinant. This is just algebraic thing. So this is very helpful, and you can compute. Okay. So tomorrow I will use this to compute Bergman kernel. Let me stop now.